Hello everyone. So welcome back to part 10 of AIML Bootcamp from Scratch. So in the previous videos, we have done the prerequisites, and in the last one, we went through a high-level architecture, high-level overview of what different machine learning algorithms are, how you can calculate the various matrices, and how are they useful in determining the efficiency of various algorithms as well. So starting from today, we'll be covering each algorithm, the important ones in detail as well. uh, with them, we'll be learning like how to choose the perfect algorithm for whatever model or whatever task you wanted to proceed on. And beside them, we'll also be focusing on like uh, how these algorithms actually work internally. So you just not only get the idea of how to choose an algorithm, but you can also refine them if you need to as per your projects, or you can use them accordingly. So just to give you a brief overview of what we have done in the last sessions and what are the different types of algorithms we have covered through. So, the number one is supervised learning, where you give the model the data and the same and the type as well. Like this data belongs to this category. Uh, Label data, we say in the terms of machine learning language. Like this data belongs to this class, this data belongs to this class. So whenever a new data comes, the model can effectively determine like, okay, I have the similar kind of data belongs to this class, so it goes there. Unsupervised, where you give all the data to the models and the model have to determine internally like, okay, this is different, and these belongs to different classes as well. So there is unsupervised, semi-supervised, self-supervised reinforcements are just mixtures. Reinforcement is just where you will tell the model like, okay, if you do this correctly, you will get a reward. If you do not do this correctly, you will get some punishment. Okay, do not like this is not a good response. So that's a way of training a model. Like if it receives positive feedback from its response, like whenever you query on ChatGPT, whenever they try to release a new model, if the users prefer the response from the newer model, it gets approval as well, based on those terminations. And for other users, if they do not feel like they get that response, that's discarded. Now, on the previous video, we have learned like feature selection, data loading, training and testing of the data preparation, model selecting, and other features as well. So these are some basic prereqs for a machine learning model, which you have to do before before you should know before actually start implementation those. Now we comes to actual learning of the models, different models, and how do they perform in their different respective environments. The first one is supervised learning. So the most used method is basically supervised learning because you have the data, you have the labels, and it helps you train the model effectively. Just a little bit costly, but some of these algorithms you study a lot in your courses as well, in your higher studies if you go around them as well, and how like you can work effectively if you're designing your own models. So let's start with them. And uh, just for your convenience, with these algorithms, we'll also be going through a live demo for how they work and how the code looks like actually. So I've been working on this thing called AlgoVisualizer, and yeah, I was just going through this. So this is the home page. If you go there, feel free to explore it, to open the workspace. There are different algorithms. We have different data sets as well. You can upload your own data set to visualize the algorithm at different steps and can see how each step proceeds and what is the actual implementation at each step. So that's something interesting. Feel free to try that out. And just to give you an overview, let's start with these. K nearest neighbors. This is the one we have to go right here. K nearest neighbors. So here is just a little bit summary, but if you want to learn about it actually, you can go to all these links, static learn link as well. So if you go to this link, Wikipedia, 10 years neighbors. So it is a supervised learning algorithms where, let's say you are given a class, or let's say a space, a data. So by giving it the data point, so you refer it to like, okay, this is the data point, and let's say suppose I want to predict uh, what can be the most, let's say, nearest possible meanings of this data. So for that, we use k nearest neighbors from where it calculates from this data point. Let's say I want three nearest neighbors, and based on that, I will predict the output. So it's used for that as well. You can refer to these guidelines. So uh, let's say we test on this data set, and for k nearest neighbor random seed, let's say we take 6, let's say 2, and I want 9 nearest neighbors of every seed. So this is the coding environment as well, a complete playground where it reflects your visualization as well. So anything you changes here will be reflected here. You can adjust accordingly, and you can like try by changing different things what happens to this algorithm and what output we get, different types of them as well, and like what are the different strategies we can follow in them. So let's start with it. Speed you can adjust. I'm taking it as one slow and start with step 1. So we have two seeds, let's say green and orange, and we for each seed we have to find the 9 nearest neighbors for each of them, and it takes 6 steps. And by the end of 6 steps, what usually happens is, okay, so based on these seed, you will get those nearest neighbors, and like you will get this is one class, this is another one. If I increase the random seeds to let's say 50, what happens? And I want 10 years neighbors. So each seed would have its own nearest neighbors as well. And by accuracy of 0.9667, uh, each neighbor is like indefinitely close with the others as well. So if you go through this data set and you will read about it in let's say detail, you will get to know the more idea based on them also. So just to give a brief overview again, k-nearest neighbors means for a particular word token, I want to know like their nearest three neighbors. That can be very handy in attention as well, where you want a variety of the data set, where you want some creativity. So you use that algorithm. Now moving towards the next, logistic regression. So there might be confusion why this is different from regression, different types of regression as well, and why it's put in the classification. Because logistic regression follows the naive Bayes formula, and let me tell you, naive Bayes formula. So naive Bayes formula simply suggests what's the happening probability of happening the event A if event B already happened, and similarly like that, vice versa. So you choose that to get the classification based on two outputs, what is the probability, and you give the result in terms of probability as well. Each model gives a result in terms of probability, but it's a simple mathematical function which you have studied in your class 11 and 12. That formula must have been familiar to many. So, moving towards logistic regression. Okay, so for that, let's say take hmm, randomly seeded and okay, so these are two different data points, so we have to separate them. So what can be the straightest line that separates them in the most refined manner? That is our task for this algorithm here. So let's say I define this learning rate 2.3 and number of full batch, let me keep it 50. So it will be good. And random seed I'll take 15. No, that will be subtract. Let's say we start from here. Okay. Now I want the straight line that clearly identified these 2 points. So I will run this algorithm, and you see the loss will be minimized at each turn. Let's see. Let's proceed. Uh, by the end of it, you will be able to get a straight line which has the minimum loss and like which is the best of the classification. Obviously, you can't classify this with the straight line irrespective. There will be some loss, but yeah, we want the best one. So for that, uh, let's say let's fast forward this a little, and you will get this at the end. Cool. This is the minimum loss we can take. Similarly, if we reduce the learning rate, it gets the same as well. But yeah, it will take much more cycles. And if we take the learning rate reasonably too high, it sometimes, uh, like let's say it's this side of the array, then it goes to this side, then go this side. So it will never reach at a certain point. So you have to choose learning rate effectively. Uh, that's somewhere middle that trains your model faster and will uh, eventually go to the local or let's say global minimum value that is have to reach. Cool. Support vector machines. Okay, support vector machines, they you draw up, let's say, as we can, here we have linear SVM, and let's go towards this. So, there you draw a kernel and a shell. So, kernel is basically pointing towards the direction to map the inputs into the higher dimensional data. And from there, like let's say, we try to get a shell which gives us the value for these different types of models. You can learn more about it as well. But yes, these two data sets and kernel minimum loss function that can be a straight line, which is at the minimum distance from these 2 points. We usually try to find that. And that's why it's called a linear classifier sometimes. Text and hypertext categorization as applications. Yeah. Whether you can read this documentation, but yeah, I would rather prefer to go to practical and the official one with HTML linear kernel. So these are the data points you have to do. Obviously, your main task is to get a line with the minimum, let's say loss, and yeah, three-dimensional law. But yeah, single one dimensional will be fine. And just initially try to interact with the playground as much as possible. Try to change the different values and see what different types of output you can get. And similarly, how these things affect your decisions, how learning rate affect your decisions, uh, and what happens at each step, how loss is minimized. So as you go by this, at the end you will get uh, the best, so or the minimum error, maximum efficiency which each model is target. Cool. So for this we have okay, we'll take those only. Uh, C value we can take 1.8. Learning rate should be 1.2. We got 70.9. Uh, yes, just that's it. So each shell and it's trying to define the kernel. Currently, it's first step. Let's see. Fast forward this. So a linear shell would be much different for this from logistic regression, anyways, because it doesn't. map in 1D. So you are seeing it as two-dimensional data structure, and from there it tries to draw a plane that is at an equal distance from both of these. So let's say this is below, this is the plane, this is above, and from there, from this plane, you have the maximum, let's say, at a distance, which is the most reasonable. Uh, yes, that will be good for this as well. And decision tree and random forest are one of the most simplest ones. Uh, okay, so by decision tree, just to give you an overview, what decision tree does is um, it maps your input into different categories. Let's say, take an example. Okay, yes. So you have to predict like, should I go and play tennis? So how are you going to predict? So first you check the weather. Like this is based on the different data you are giving and different outputs. So from this, okay, this one will look good. Yes, play golf. So based on different values and sets you are given, and from there you have to like predict whether you're going to play golf or not. So from this, the outlook has the highest weightage because its decision at the root level, which impacts the tree maximally. You will keep that at the root level, and other things go down as the leaf. The least impacting one will get the leaf. So by weather condition, to determine if it's sunny, you will see if it's windy or not. If it's overcast, you can see overcast, yes, overcast, yes, overcast, yes, overcast, yes. So one, when there is overcast, you'll go and play golf. It's as clear as that. So you will do overcast. If the condition is overcast, you will go and play golf. Now there are two more conditions, sunny and rainy. So for rainy, you can see temperature is not the condition. We'll cover that later. If humidity high, no. If humidity normal, yes. And similarly, humidity matters if you are talking about the rainy conditions. For sunny, humidity normal, yes. Sunny humidity high, no. Sunny humidity high, yes. Sunny humidity normal, no, as well. So in sunny, humidity doesn't play an effect because for high humidity you are getting a yes and no. For normal, you are getting a yes and no. If you don't take that into sunny, you take that into rainy, where the fractions are clear. So if the humidity is high, you don't go and play golf. Humidity is normal, you go and play golf, yes. Now coming towards the windy conditions for sunny, similarly, these are affected by the winds. If the condition is windy, you go and play golf, yes. No, if windy conditions, you do not go and play golf. If the conditions are not windy, you go and play golf. So by this decision tree, you will get output like, okay, if it's outlook, rainy, humidity is high, let's say, I don't know. This is a simple presentation of this data. You will, that should do good. And yeah, if you just try to go into this and start based on this, it calculates different nodes based on their weighting. So it calculates nodes, one deterministic, x0 greater than less than 5.4. If it's greater than plus 0, if it's less than x0 less than 0.55, and here you will get different outputs based on that. Simple as that. The next one will be random forest. So what does random forest do? It's a, let's say, advanced version of classification algorithm. In this, you have multiple decision trees coordinating with each other to give you the final output. And from while traversing through one decision tree, you get a chance. You do not get chance to go reverse in decision tree. If you go towards one node, you cannot go back. But in random forest, you can go back at a certain node as well in certain iteration. That is what advantage over decision tree. So if we take that and let's say we try to run that algorithm, uh, by the time of activity and forest, it's much more like that. You get here different trees orchestrating with each other, and each tree you're getting a different output. There you will having a sigmoidal function, and from there you are calculating the final output. If you want to go back, this function will point at a specific node. You can customize it, modify it as per your needs. This node can communicate with this node as well. This node can communicate with this node as well. So internally, you can have a lot of checks. And after once you get a final output, you can map it accordingly. And based on that, you will get a desired output which you can map. You don't see a different trees. But yeah, that's how you categorize with the minimum loss. Yes. Accuracy is 0.98 because we can see these two data are pretty different clustered and these are out. So there are 10 different trees with depth of 4. Do not actually see them because it's 1D space. If you get a 2D, you will see them lying underneath with each other, communicating. Good. So while here you try to make sure have on the playground, like let's say if I have two trees. Now let's what happens. Oh, he has 0 there. Let's show. Okay, what do I define the step there? So there you go. Each tree different classified differently, and with each step you will get a higher result. So less trees we are getting a 0.99 accuracy. That's much higher than the previous one. And select features, and yeah, if you try to map them, you will get out. Gradient boost that works on specific formulas. Um, Let me just take you through there. And forest with gradient boost. So what gradient boost actually does is it will take your output from each, and from there it transfers a model function or some kind of function internally, and based on that it will give you an enriched output learning rate parameter or something like that. From there uh, you run to refine your trees, like let's say it's on top of random forest. uh, where yeah, let me just get the formula. Yes, this is the formula. Lambda, okay, this is basically your regularization parameters. You regularize so that you don't overfit the tree, you don't overtrain on the certain set of data. To avoid overfitting, you do all these steps. Category features, yes, that will work as well. That's yes. So that is very much like, and if we go to number of tools, let's say 10, learning with 0.2, that will work fine. Same, because we don't have the tab to the gradient boosting function is not controlled. It's currently predicting the separate output, but yeah, for large amount of data sets where you have a large chance of overfitting and let's say underfitting as well, where you need regularization, you need different stuff as well. So their gradient boost comes in handy. Uh, if you have, let's yes, I don't think shapes can work, I guess. Yes, that might eventually work. loss is 0.5. That's still high. But yeah, it takes time. So, if somehow we can increase some of the iterations, I don't think so we can for this. Yeah. So, you get an idea of how gradient boost works, and by this, um, you can get the idea for different aspects as well. Okay, so moving ahead, what is the next part after classification? We move towards the regression. Regression is just basically like what would be the actual price of this house in 2028? Let's say annual growth is 10% and condition several factors as well. So to calculate something mathematically based on certain factors around them is called regression. Just high level overview. So in this we have different types of, let's say, algorithms: linear regression, polynomial, class average, plastic net regularization as well. So these are each useful in its different set, its different segment, and why they are useful, we covered that as well. So starting with, let's say, linear regression. So for this, I guess, yes, linear trend, obviously, you want to see a straight line that goes like this. This is simple. Like based on x and y axis, what should be the mass straight line? Let's say start from here. And learning rate 0.05 would work fine. As we have a slow learning rate, it moves slowly towards the desired goal. And if we increase the learning rate, we'll see the actual movements are faster. But yeah, it might skip the global maxima and global minima of error to the global maxima of, let's say, performance. Okay, we are constantly in the loss. Let's see, 5, 4, 7, 4, 6, 4, 5. Okay, the loss here is constant for 4. Yeah, let us simplify. The most simple representation of regression what is, as x-axis move this way, y-axis move this way. Simple. And if we move towards next with polynomial regression, linear is just basically based on 2. Now if we come towards polynomial, and let's say we have degree of 4, and yeah, that would be a curve actually, the degree of 4. Okay, I think that would do good. So how you adjust the curve? And for degree of 2, that would be parabola. Okay, it's like shifting that parabola more towards like this. So, polynomial regression is actually, let's understand, where y is dependent, output field which we wanted to get is dependent on one variable, but it's different degrees. Let's say x square, x cube, on a certain amount. Um, when it will depend on x square, let's assume, uh, okay, let's assume for spam non-spam filtering or medical filtering, it can depend on high degrees as well. Like if it gets this, it gets a lot more high weightage, square weightage or something like that. So to the power of t, those Celsius steps, you will get that simple coding how will like eventually display and what we will use to eventually find the minimum loss. So once we done with this, we get the final output like this. Just to be crystal clear, we go for linear. Let's have a wave. Yes, that would move 2, and for degree, let's assume we have 5. See how easily it maps to this degree. And suppose if you have parabola, it will have to like map like this, something short of this. Okay, now this is what I'm telling. It as a learning rate might be too high for this. Let's just make it a little. Okay, Let's see how it goes now. We intend to see less creative if we have a low learning rate. That's how. Because we are intending to find out the global minima more effectively. And if you just fast forward it, yeah, that will be actual 425. Full regression is a simple lasso and ridge. Lasso is just least absolute shrinkage, and that let's say, okay, we have a method called least squares, and what it does is it will add a penalty to them so that it makes them shrinking towards zero. Uh, okay, if we go here, uh, so lasso and bridge. It is and not sine wave, we get noise, yes. So just to get a brief overview of what lasso and ridges are, least squares is a method we use to find the errors. So what it does is it find the gap technically and set a regress parameter to get something based on let's say the model to eventually get you the result which is actually in between the desired output and the minimum. So it tries to get uh, let's say between various performances and to try to give you the output that fits the situation most effective. We get this, and if we try the which, okay, the which is somewhat similar parity based, but this is not L2 regularization. It intends to uh, reduce the model complexity. So if the model is too complex, we are moving towards overfitting. Okay, so it reduces the model complexity and to get the L2 regression. With L1, we move towards underfitting. With L2, we move towards overfitting, reduce by reducing them. So it's important that we move towards that direction. Cool, that worked fine. And if we fast forward, we get the similar idea. Not the similar output to Elasto because for complex data, as this is a noisy data, there the best would be to use the complexity. No. Okay, Elasto would work better. So this is not the output you want. Rich is not the correct for this. For simpler one, Rich is correct. For the complex one, you have to choose the lasso model. Elastic net regularization, this is also a form of regularization where you get, I guess, L2, 500% sure. Okay. Okay, with both L1 and L2. So it tends to find the best of both the parameters and it finds the best of the possible. So let's say it has to align more with last. For faster with this. Yes. So that's how we get the output. So these are just regression and classification algorithms. You can read about them in detail as well. You can try the playground. You can try like if we change various aspects, how it affects the data, how it affects the random parameters and everything. You can try the ratio to base algorithms to choose who gets there faster, like one algorithm to algorithm. We are done with them. We have to go to unsupervised. We will start with unsupervised after this. So yes. So coming to unsupervised algorithm, that is basically two types. Clustering and dimension reduction. Clustering basically you get different types of data. Okay. Now the one question arises in your mind Supervised learning algorithm is there. We get the label data and we get predict the output as well to the label. What is the need of unsupervised learning? Because supervised learning is expensive, you have to provide the label to each data as well in the training phase. And for unsupervised learning, you don't have to provide any of the, let's say, label. You get the data and it will, based on the best of its knowledge, what it does is it classifies it accordingly into different segments or groups and it creates the data accordingly. So that's why unsupervised data or let's say unlabeled data is used very often as in combination to supervised because it reduces the cost of training and it's very helpful if you want to just categorize or do another thing which is dimensional reduction. So let's say if you get a very complex data and you want it in simpler forms, unsupervised learning dimensional reduction like PCA is very much used. Autoencoders is used heavily in the transformers and various segments. So we'll cover them as well. Now coming towards with clustering. Okay, so exclusive for overlapping hierarchical probability. So one of the most uh, used clustering algorithm is K-means. That's a simple. You want to have this much of clusters, and each cluster have its this is a scattered data, and you want that into the group of let's say I want that in group of 6. And each cluster should have data of its different types. And let's say I choose this mapping. 3 here, 1 here, 2 here. How how different clusters will be formed and let's say max iterations I'm taking to 50. So at the end of 50 iteration, or if two clusters are repeated, it will stop eventually. Currently, 3, 1 is there. As the points of this uh, are closer to this cluster than this, it will not move ahead. Good. So if you think, I guess that's one of the points. Yeah, but let's say this only these 3 have divided clusters here, these 2 are divided here. Simple. If two are there, these are divided by these 2 are divided, these 2 are divided. And at the end of each cluster, the center point has to be in the centroid, and from there it maps like if this point is closer to this or this, and whoever is closer, whoever centroid is closer, that points move towards that cluster for that iteration. Okay, so yes, next we have DBSCAN. Okay, it's just uh, okay, DBSCAN is more like density-based spatial clustering. So, whoever has a higher density, it gets one point allocated. Similarly this. So for k-means, you specify how much clusters you want. Density, you do not specify that. The dense regions are automatically clustered into one. Here also. So it's not in your hands to determine, let's say, the density. You can adjust the radius. Let's say if I keep the radius as well. And these points do not get into any clusters. That might be center and all those points. So if you reduce the radius, you can see a lot of points will not be a part of the cluster. See, simple. Hierarchical clustering is okay, 3 would be good, as the name suggests. That's some random suit. Okay, it's functionality. Okay, we started with 3 single collect clusters, and at the end of each iteration, we map each other to the closest point. And if they are together, similarly they get merged. Okay, how do we actually get there? Cool. And this get grayed out, and at the end of that, you'll get the clusters. So feel free to go through this in detail as well at each step. But yeah, this is a condition where you have to use when you have a much complex data for defining the clusters hierarchy. And probabilistic is just Gaussian mixture model. Let's say three clusters, and I want the density is empty just to get to a good idea. And cool. So GMM is basically a technique which uh, uh, let's say do not operate in one dimensional space. So you see this one is just like this, one is like this, and the other is like okay. So it tries to cover every of the points possible into let's say different regions. The cluster green points together, the gray points together at one, and yellow at one. So blocks is not the perfect to yeah. So if it is scattered, how you cluster them into three components? Here k-means will not work very well. So yeah, you have different, let's say, uh, mixture models that covers in space, adjust the shapes accordingly, and tries to cover all of the data points. So by the end, you will get out of simple as that. Okay, so yeah, we are good with clustering as well. Now we come towards dimensional reduction. What are the different algorithms for it, and what is reinforcement learning? Okay, so dimensional reduction, as I mentioned, like when you have a let's say certain data in high dimensions, let's say 4D, 5D, you want that to lower dimensions like let's say 2D or 3D, you use dimensional reduction algorithms. One of the most common is PCA, principal component analysis, and it is used to reduce the number of let's say variables dependent in a dataset while preserving the most important information. How it does is it transfers the set of variables that are already there into a set of new variables, uh, and we call them principal components. And then, like based on them, we try to find the new equation or something else. And thus, by preserving the most important information, we reduce the number of variables. The variables in the end, which are not required that much, uh, let's say we can skip them. Let's just try our overview. And if we go through yeah, PCA, and okay, it works on that as well. Let's say shares. So, okay, if you have these shapes, how are you going to reduce the dimensions? That's a horizontal, vertical, and diagonal. Similar, green at this. Yellow is not required because it is clustered in position. Similarly, as this captures the most important field, this is the most, and all the yellow points you see, if we cover this region, if we cover this region, all the yellow points are covered. So from this we have covered everything, and diagonal we are not required. It goes as simple as like that. It is very useful while dealing with complex algorithms, as you don't want to compute the results of various complex algorithms because somehow it is interconnected to the cost. If you compute the complex too much, the cost will be higher, and that is not required. So you want something that is cheaper, computes less power, and gives the maximum desired output. So for that, if dimensions are required to be reduced, we use PC. As simple as that, if we will run different data set as well, let's say an isotropic. Purple is much, then green, cluster 1, cluster 2, cluster 3. scores the maximum region, and this is the second most. Simple as that. And the next one is not TSME. You can check it out yourself. Autoencoder is one of the most important algorithms, I must say, because it comes with neural networks as it is used transformers as well. Um, what it does is, let's say we have input data in set of various vectors, and it converts them into a low-dimensional code and restructuring the original input, as mentioned here, from the representation. And autoencoders can deliver features and reduce the dimensionality of the data, making it easier to process and analyze. Okay, so if we get an input vector, let's say various dimensions, how you're going to reduce the dimensions, what critical informations are there that need to be passed, and if we can compress this or not. All these are done by autoencoders. So for them, let's say, let's use the various density blocks. And if we can go to the end, simple. This is another cluster that is formed, second and third one. So that is the most scattered, and this one is the maximum number. This has the least as indicated, and this is the second most as based on the initial cluster. If you look at the initial stage, so this is the data, and it has to be covered all the spaces because we have to analyze all the aspects while using autoencoder. Because in neural networks, you have the bias, you have the weights from other vectors as well. We have to process them simultaneously, and then based on them, we have to analyze the data as well. Simple as that. Yes. Okay. Yeah, let's read that. And what does our documentation suggest? A PDF and a research paper. Okay. So whenever you get a chance to read a paper about a certain algorithm, feel free to read it. Just read the abstract, and just by reading the starting few lines, you will get the most idea why this algorithm is required. And you can register and read that for free. High-dimensional data can be converted by training a multilinear to a small central layer to reconstruct high-dimensional input vectors. So if input weights are close to a solution, this line is over. Yeah, that is okay. It is more useful while you are initializing your weights and you need something that can reduce the dimensions for the upcoming input vectors to the greatest required output. That's the subsystem. You can register, create an account, and yeah, read that for free as well. Cool. Uh, so yeah, we are done with dimension reduction with that. And now moving ahead, we have reinforcement learning. Reinforcement learning, as the name suggests, and previously mentioned by this algorithm focus heavily on reward or punishment. If the output is desired, you will get reward. If the output is not desired, you will get punishment. Let's say the output is not required, not interested, dislike, something like that. So here we have four: deep view, policy gradient, actor critic, true learning. True learning is the one which is heavily used. Here we have this data. Okay, so that's a simple quiz. If you reach the output by performing any number of actions, you can change the number. And you want to take the, let's say, output in the minimum steps. So reward is, if it's positive, it's great. If it's positive, high, it's great. If it's negative, much lower, then it's not required. So it will go like that to start and end. And now it's just to the way. So just to give you an idea of what Q-learning is, uh, to okay. So in the current state, it's asking the agent to assign values to these so that we can have the minimum traversal path. One can be this as well. and this can do good as well. But yeah, minimum traversal part by making the minimum number of changes. So in the path, so it tells the model like make this that much number of changes less, and want to find the most possible path, and where you would have the highest reward function, it will choose that only. Simple as that. You can read about it. The research paper link is already there. Feel free to go and yeah. Okay, so next we have deep networks. So that's just somehow linked to learning as well. If I just fast forward, it creates this. Why? Because it's a uh, reinforcement learning and deep. Okay, deep learning into solution allowing just one decision from abstraction to data while manually engineering of the state space. Okay, let's see. Deep RL is trying to find the path which is the least uh, least weighted, and let's say there you have to make the least number of changes and like least number of calculations. So the agents always try to find the least path. So one could be this, one could be this. As we have a T, we cannot move in this space. So one could be this. So here it will have to make a lot of changes. Then the model does not suggest it. So in order to skip that, it tries to take a simple path as much simple as possible towards the end goal. Starting from there, making the least number of let's say changes, and from there it goes towards the desired part. If we take an example of maze as well, simple. It takes into account the deep learning algorithms as well for let's say relying heavily uh, on the computation. Cool. Yeah, that should be good. And similarly, if we move towards reinforcement learning, there is a simple reward punishment. It tries to predict at each step. It gets the output is fine. If it's not getting the output, yeah, it gets the reward will keep on computing till the very end. A simple step. It takes a lot of computation. Here you will see reward getting minus as well because I will try to compute various steps. If it's no, it's going in the negative direction. So it comes back if immediately. And from there, it tries to stick with source nil path. As simple as that, it relies on simple formula where we are calculating log of its current state over the like past state. And from there, we are calculating the gamma return function, which you can say the learning rate, or let's say the error. So if the error is in the negative, it starts towards that path, and if it's in the positive direction, it tries to take that path, and from there, it tries to move forward as well. So, activity. Let's say our sparse between. See, it also takes final output goes here because yeah, should try to calculate the reward, the negative direction. It tries to explore all the paths. But yeah, simple and lightweight framework. Okay, it is also gradient descent. So towards the minimum loss function and by optimizing of neural network controllers. And for variants like let's say you can use it as Q-learning as well because it is lightweighted and it relies heavily on framework. So yeah, it works fine for data which is less complex. Let's say if you take something like 4 by 4 grid, it will do good here. So it will try to get calculate output from all aspects. And if we go to the end, yeah, simple. simplest path available and simplest path taken. Much more like that. So that's some higher level overview, and this is about the website which I just basically building. So you can try to learn more about the algorithms from research papers, from Wikipedia, from different sources, and like you can learn more about these algorithms. But yeah, it's just helpful visual understanding. The code is here in front of you. Try to make these changes. Try to play around a little with the playground, like see how different things, let's say, change the whole aspect of the outcome as well. So while you do all those stuff, you will be strongly aligned to, okay, this happens if I do this happens if I do this, these are the things that I have to avoid. And you will come to know a lot of things while you read the research papers, while you, let's say, try and do hands-on stuff on coding as well. So feel free to explore this. I will paste the link of this in description as well. And yeah, these are some of the basic of the algorithms. These are mostly used while building some models, but yeah, why they are used to, what all these matrices we have covered, but we will cover them in detail as well. So you should be knowing all those algorithms because moving from deep learning and various algorithms, the mathematical formula behind them and everything behind them, that should be known, that should be that. But it's not that much difficult. You will understand them. Just go there and take a look, take a deep look over it, and it will be just fine. Cool. So supervised learning all these algorithms and supervised and reinforcement. The important ones are KNN, sub SVM. Uh, Classification all are important. Regression, linear regression, and elastic reg will be fine. Clustering, you have to do all for DBSCAN, hierarchical probabilistic. Here you have to do PCA and autoencoders, both are useful. And for reinforcement, Q learning and deep Q networks, that will be fine. So if you do these algorithms by heart to understand the formula behind them and how, let's say, computation happens behind and how we get the actual output, how learning rate and different parameters affects the output, it will be doing just well. In the next video, we will cover all those aspects and we'll try to start with deep learning techniques as well. And pardon me for like delay uploads of those videos because a lot of things been happening and a lot of things I've been trying to do as well. So if you think anything that is required, you can ask the questions. And if you think you need a video on certain specific topic earlier, feel free to mention that. I will try to post on it as soon as possible. Uh, and by the time, like try and explore, learn as much as you can, read the research papers of whatever text like you're moving forward to, and try to play with the background as well. So you can, yeah, post on social media as well, hashtag with group, and yeah, will be good, I guess. So keep learning and yeah, make sure you learn effectively by doing, not relying on AI while learning, and yeah, feel focused and do it nicely. So take care. Bye bye. Good night.